Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back to Optimization in Civil Engineering. In the last class, we discussed about multivariable optimization with inequality constraints. In that process, we saw how we can convert the inequality constraint into an equality constraint by adding the slack variables. And once we had added the slack variables, it becomes simple and we could actually use the Lagrange multipliers in that and come up with the solution. However, in the process, we also found out that the number of equations that need to be solved for the solution had increased from n plus m, which was there in the equality constraint. Now it has become n plus 2m, where m stands for the number of constraints and n stands for the number of variables. Then we came to a point where we said certain constraints might not be active. So if we can consider the active constraints only, we could easily show the number of equations to solve the problem can be again reduced to n plus m, where n stands for the number of variables and m stands for the number of constraints. However, in that process, we need to find out the active constraints. Once we can find out the active constraints, then within the active constraint we can actually find out a feasible direction in which, if we search, we can easily obtain the optimum solution. We had followed through with an example and we had shown you how we can find the optimum solution location and the criteria by moving from one of the point where the certain constraints were active, and from there we moved to other feasible location where other constraints were active. So that was in the last class, and we always felt that identifying the active constraint could be quite involving, or it could be quite difficult, particularly if you have many constraints or the optimization problem is quite complex. So today we are going to discuss about the Kuhn-Tucker conditions which can help us to solve the multivariable optimization problem with inequality constraints, particularly in certain situation. So let's see how we can use the Kuhn-Tucker conditions effectively to solve such problem. Let us first refresh our memory on the multivariable optimization problem with inequality constraints. As we had said earlier, the multivariable optimization problem with inequality constraints can be represented as the objective function which needs to be minimized or maximized with the constraints, particularly the inequality constraints of this nature, where the constraint function is less equal to 0. In this optimization problem, we have n number of variables and m number of constraints. Then we use the slack variable to convert the inequality constraints into equality constraints, and as we introduce the slack variable, the constraint equation is going to look like this, where my yj square is my slack variable. After conversion, the optimization problem can be represented in this form, where fx is as usual being minimized or maximized with the constraint function which has now the slack variable y as well, and this is going to be of this nature, which is going to be equal to 0. And as we had introduced the slack variable, now in this constraint equation we have m number of slack variables. Now with this optimization problem, the converted optimization problem, if we try to use the Lagrange multiplier, we can easily convert it as follows. First of all, the Lagrange function is going to look like this, where we have three different variables right now. This is my decision variable or the design variable. This is my slack variable, and this is my Lagrange multiplier. As I said, this is my design variable. So this Lagrange function is going to have the three different type of variable, and if we look into the necessary conditions, we are going to obtain three different sets of equation in the necessary conditions. So the first set of equations are related to the partial derivation of the Lagrange function with respect to the design variables, which is shown here, and this is going to yield n number of equations, which is equal to the number of variables. The second set of necessary conditions is going to yield the partial derivative of the Lagrange function with respect to the Lagrange multiplier, and this is going to yield my equality constraint along with the slack variable, and here we are going to have m such equations. The third set is represented by the partial derivative of Lagrange function with respect to the slack variable, and it is going to look like this. Again, we have m number of slack variables, so the number of equations we can obtain here is going to be m. Now, in this particular condition, in our earlier class, we saw that since this is a multiplication of my Lagrange multiplier and the slack variable, and which is going to be equal to 0, so one of them is going to be equal to 0, and if one of them is going to be equal to 0, then we have a different understanding on that. Particularly if the Lagrange multiplier is equal to 0, which is this, if this becomes 0, then it indicates that my constraint is inactive. On the other hand, if the slack variable tends to be 0, it indicates that my constraint is active, which means my solution is going to lie on the extreme value of the constraint. That is when my constraint is going to be equal to 0. So with this understanding, let us now understand the Kuhn-Tucker conditions. So in the Kuhn-Tucker conditions, at a constraint optimum point, which is my x star, the first set of necessary condition for the active constraints only is going to yield this set of equations. In this, as I said, since these are my active set of necessary condition equations, the lambda j are going to be greater than 0. In case the problem is a minimization problem, and in case it is a maximization problem, my lambda j is going to be less than 0. So this condition is only true for the convex programming problem, where the objective function and the constraints are convex, and Kuhn-Tuckers had proven that in that type of problem, the necessary and the sufficient conditions are same for a global optima point. So these are the Kuhn-Tucker conditions. Now in this process, as you had seen here, we have to identify the active constraints. So this is applicable for the active constraints. As I had indicated earlier, identifying the active constraints is also quite involving. So we need to understand, or we need to develop a method where we do not need to identify the active constraints. Rather, we can use all the constraints and see if we can tweak this method to come up with the similar result. So in this format, we are saying that if my active constraints are unknown, we can consider the complete set of constraints. So the partial derivative of the Lagrange function is going to yield this, where we are not differentiating with the active or inactive constraints. So it includes both active plus inactive constraints. So once we include the both type of constraints, then we definitely need to ensure that this condition is also there, which will take care the inactive constraint part, so that the equation becomes 0. Then we also know that our constraints are less equal to 0. So these three things together can help us to identify, or can help us to solve the multivariable optimization problem with inequality constraint using Kuhn-Tucker conditions. Earlier we had said if we are only looking into the active constraints, my Lagrange multipliers are expected to be greater than 0 in case of a minimization problem and less than 0 in case of maximization problem. So if the standard formulation, if we are trying to use it for the maximization problem, then my lambda was supposed to be less than 0, and in this case we have used both active and inactive constraints. In case of inactive constraints, I know my lambda values are going to be equal to 0. So in this particular case, now we are saying lambda values are going to be less equal to 0. In other words, we are saying those are non-positive values. In case my constraint, which was less equal to 0 in nature, changes to greater equal to 0 for the minimization problem, the same rule applies, means my lambda values are going to be less equal to 0 or non-positive. In the other cases, like if it is my maximization problem, as well as my constraints are going to be equal to or greater equal to 0 instead of lesser equal to 0, which is shown here, in that case it is going to be non-negative, which is equivalent to the minimization problem. The lambda values were supposed to be greater equal to 0. So we are saying in this case greater equal to 0 or non-negative. So in case of minimization problem with this standard format, or in case of maximization problem with a change in my constraint, my lambda values are expected to be non-negative, which is lambda j is expected to be greater equal to 0. In case of minimization problem with the constraints greater equal to 0, or the maximization problem with constraints lesser equal to 0, my lambda values are going to be non-positive. That means my lambda values are going to be less or equal to 0. So this is the generalization of the Kuhn-Tucker conditions which we discussed in the previous slide, and in these particular cases we can actually consider both active and inactive constraints together to come up with, which means we do not have to identify the active constraints to conclude whether we have reached the minimum or the maximum point or the minimum or the maximum function value. However, as I said earlier, the optimization problem must be convex, which means the objective function as well as the constraints are supposed to be convex function. Now we'll try to understand this thing with an example. Here is the example where we want to minimize this particular function for these two inequality constraints. This is quite clear. It is a circle whose center is at 1, 0, and these are the two constraints which are of the third order polynomial, and both are less equal to 0. So to solve this problem, first of all we need to go through the process of the Kuhn-Tucker conditions, and as I said, for unknown active constraint set we need to first find out the set of equations which we have in hand. For that we need to derive the partial derivative of the Lagrange function with respect to the design variable or decision variables, and these are going to be these three set, and these three set, if we represent it with the help of the Lagrange multiplier, we are going to obtain equation number 1, which we are taking this component, this one and this one, and if we do the simplification of that, we can obtain this one, which we are indicating as equation 1. The second part of the equation is formed using this component, this one and this one, which is shown here, and once we transform it we can obtain the equation 2. The third part was that once we multiply the Lagrange multiplier with the constraint, it is supposed to be 0, so that is what we are doing. The Lagrange multiplier multiplied with the constraint, and it is going to be equal to 0. So this is my third equation. For the second constraint we are doing the same thing, which is yielding the fourth equation. We had one more condition, which was my constraint value should be met at the optimum point. We'll use that in the next process. So now with this understanding we have 4 equations, 1, 2, 3 and 4. These 4 equations we'll try to solve to obtain or to find the values of the design variables x1 and x2, as well as to obtain the value of Lagrange multiplier lambda 1 and lambda 2. So let's look into the next step of the solution process. In this process we are starting with an assumption that both my lambda values are equal to 0, which is indicating that none of my constraints are active. In that case, if I use those equation 1 and 2, then I'll obtain the solution as x1 is equal to 1 and x2 is equal to 0. We'll decide on this thing at the later stage. Second, we are looking into the condition when one of the constraint, particularly in this case the first constraint, is equal to 0, which means that is inactive, but the second one is not equal to 0, which means the second one is an active constraint. And again, if we make it not equal to 0, then we can use the equation 4 to come up with the relationship between the two design variables, and then we use that value in the equation 2 to find out the value of my lambda 2, and subsequently replacing it in the equation 1, we can rewrite the equation in this form. This is a fifth order polynomial, and if we solve this equation for the real roots, then we can obtain the x1 value as this. and if we replace the x1 value here, we can obtain my x2 value as this, which is negative 0.239, and once we get this, as we replace the value into this one, then we can obtain the lambda 2 value as 0.239, which is indicating that the lambda value is more than 0. In other words, if this condition is true, then we can say we have reached to a minimum point. We need further discussion on this. We'll come to the later after we look into all the 4 cases which we can have as part of our solution. So the other assumption could be, when my first constraint is active, my second constraint is not. In that case, again from equation 3 we can get a relationship between the two design variables, which if we replace it in equation 2, we can obtain the value of the lambda 1, and once we replace it in the equation 1, again we are going to obtain a fifth order polynomial with respect to the design variable 1, and solving that we can get the real value of the, or if we take the real value of the constraint, this is the same value which you obtained in case of case B. However, once we replace this in the equation 3 here, the x2 value is going to be the positive value of 0.239. Earlier it was, in case B it was negative, now in this case it is positive, and the corresponding lambda value, this is going to be lambda 1 value is going to be 0.239, and again it is indicating that the obtained solution is the minimum for this particular condition. The third case could be where both my constraints are active, and in this case, if we solve equation 3 and 4, we can easily obtain the value of the two design variables as equal to 0, and as we replace these values in those equations, we can show that the two Lagrange multipliers are going to be equal. It indicates that the lambda values can take both negative and positive. If lambda 1 is positive, lambda 2 is also going to be positive. If lambda 1 is negative, then this is going to be negative. So it is kind of a position where we cannot decide, or we cannot conclude whether my solution is the maximum or the minimum. We are going to discuss about this further, but in general we can say from the Kuhn-Tucker conditions that if we reach this condition, the KT condition is not satisfied. So for this reason, let us look into the graphical representation of the problem. The graphical representation of the problem can be as follows. We have the two constraints. Here it is shown in the blue line, which is my first constraint, and in the first constraint we said less than equal to 0. So this is the infeasible region for this blue line. I am marking the infeasible region. So inside of that, on the other side of that blue line is the feasible region. The orange line represents the second constraint, and since that was also less than 0, this is part of the line is going to be infeasible, which indicates that the other side, which is of this part, is feasible. Now if you look closely, we see that these two constraints are meeting at one point here. And now let us look into the objective function. The objective function surface looks like this, and the lowest point of this objective function I can clearly see is going to be here. The same figure is represented in the two-dimensional way in this particular image. This is the two-dimensional, and we represent the function values of the objective function as the contour lines, which you see as the circle whose center is here. And if you recall, while describing the problem, we said the center is at 1, 0, which is this point. And if we look into the constraints, my constraints feasible region is this part and this part. So my minimum point is outside my feasible region of the constraints. And as it is clear from here, these two constraints are meeting at only one point, which is here. So with this understanding, let us see the different results we have obtained. So in the case A, we said both constraints are inactive. So when we say both constraints are inactive, means my constraint 1 and the constraint 2 have no effect on the solution. If these two constraints have no effect, my solution is going to be the true minimum or the global minimum of the objective function, which is here. And this is the same solution if we consider the problem as unconstrained multivariable optimization problem. But in this particular problem, we have to consider the constraints. So let us look into the next option. If we say that constraint 1 is inactive but constraint 2 is active. When we say the constraint is active, which means we are saying my solution is going to lie along the boundary of the constraint, which in this case for the constraint 1 is this blue line, and constraint 2 is this orange line. So this is the extreme case when it becomes active. Now if my solution lies somewhere inside, suppose if this constraint was not there, my constraint 1 was not there, if this is not there, if I have only one constraint, my solution can lie within this point. If it lies within this point, not for this objective function though, but in certain other objective function, if my point lies inside it, then again my constraint is not as such active, but it is satisfied. So that is the reason we left out one component, whether the constraint is satisfied or not, in the previous slide. Now we are going to check whether it has been satisfied or not in this process. So when we look into this, as I said, my constraint 1 is not active, which means suppose this is not there. However, my constraint 2 is active. We obtain the solution as x1 equal to 0.781 and x2 equal to negative 0.239. It indicates point somewhere very close to here. And if you can see, this is the lowest point which we can obtain if this constraint was not there. Only this constraint was there for the objective function, which is kind of circle. So if we are finding out the objective function of the circle, the contour would look like something like this. And this is the lowest value which we can obtain for this constraint.